time. Very good. Our next speaker will be Astrid Eichhorn from Heidelberg again, right?
Yeah.
Back in Heidelberg.
Indeed. Yes.
And she will tell us about quantum gravity at all scales. So please go ahead.
Yeah, so thanks to the organizers for the kind invitation. So indeed, I'm talking about probing quantum gravity at all scales. So this might seem a little bit out of the scope of the quantum field theory session, but you will see during the talk that most of what I will have to say actually fits perfectly into sort of a standard QFT. All right, so the motivation is the following. We need a quantum theory of gravity to answer some of the most profound questions about our universe. What is its very origin? What's the true nature of black holes? What is actually the deep quantum structure of space-time? And in response to these questions, candidate quantum theories of gravity have been developed, including, for instance, asymptotic safety, loop quantum gravity, string theory, and others. The challenge, however, is that we don't really know how to test which of the proposed answers are correct, because most of what these theories have to say is a priori about the Planck scale, and the Planck scale is quite a bit removed from experiments. So the key challenge in this field is that there is this gap in scales between the Planckian scales that we are interested in, and then the scales in particle physics, black holes, and cosmology that we do actually have direct observational access to. So what's the best strategy here? Should we just give up and wait a few centuries for technology to catch up? Well, that's clearly not the most satisfying thing to do. Rather, I think what we should be working on is to develop sort of lever arms that allow us to take an effect at the Planck scale that a priori is sort of a teeny tiny effect, but it enhance it in a suitable way so that we can actually access it at experimentally accessible scales. And there are examples of such lever arms. For instance, in astrophysics, you can use astrophysical propagation distances as a lever arm to take a very tiny effect that would come from a quantum gravity-induced violation of Lorentz symmetry. And then this accumulates over a long propagation time, and in this way it becomes something that is macroscopically measurable. And this is the basis to actually constrain Lorentz invariance violation even to beyond the Planck scale. So this is a very successful example of a lever arm. There are then a few others, some of which I've listed. But in this talk, I will actually be using the renormalization group flow of couplings, so just a sort of standard QFT concept, as a lever arm to bridge the scales. So what's the main idea here? The main idea is as follows. So what the renormalization group flow allows us to do is to understand how couplings evolve as a function of scale, which we typically think of as energy scale. And now assume that we have a quantum gravity regime, and out of this we get a prediction for the value of some coupling. That will be a prediction at the Planck scale that in that form is not very useful because we don't actually have experiments at the Planck scale directly. But then the renormalization group flow allows us to calculate what the corresponding value of the coupling is at whatever lower scales we do actually have access to that particular system. So it provides us with a corresponding prediction at the scales of experiments. Of course, under the assumption that there isn't anything at sort of intervening scales that would change this renormalization group flow. If there is something at intermediate scales, of course, you have to account for the corresponding effects as well, and then this picture here will change. All right, so that's the main idea. Now, in order to make this work, what do we need? Well, we do need predictions of couplings at the Planck scale. And there are some quantum gravity approaches that do that for us, in particular when it comes to the couplings of particle physics that we can then at much lower scales probe in particle accelerators. So one example is string theory, and then also the stringy swampland conjectures is of course very much aimed at this idea of constraining large-scale physics from the underlying small-scale physics. Second example is asymptotically safe quantum gravity, and then you see there's a little bit in causal sets, but then mainly this is also an open opportunity for other quantum gravity approaches that hasn't yet been exploited very much. And in this talk, just to sort of give you a concrete example of where these type of ideas can lead you, I will be focusing on asymptotically safe gravity, which is a quantum field theoretic approach to quantum gravity and therefore fits very well into the quantum field theory session. Now, many of you have probably heard a little bit about asymptotically safe quantum gravity, but nevertheless, I'll give you a lightning introduction into what it is. So the key idea of asymptotic safety is that there is a fundamental symmetry, scale symmetry. So space-time basically becomes self-similar, sort of, and like this sort of fractal object that I've shown down here. But it's a quantum version of scale symmetry, which means that it arises due to the effect of quantum fluctuations, and it means that the renormalization group flow, which in general is non-trivial in particle physics, if we look at microscopic scales, we actually start out in a regime where all couplings just assume constant values, and then somewhere below the Planck scale, they actually start to depend on the scale. And so then microscopically, our world below the Planck scale and much further below just in some sense becomes the self-similar system. So that's the general idea of asymptotic safety, can be applied in principle to any type of quantum field theory and is realized in many different non-gravitational quantum field theories. But in particular, we are interested in applying it to gravity. So then we take a gravitational action for the metric, and we include not just the Einstein-Hilbert term here with cosmological constant and with the Newton term, but we also include all of the higher order operators that you would also get if you would start to do perturbative renormalization of quantum gravity. And then you have to promote all of these couplings to their scale-dependent running counterparts. And asymptotic safety then says that all of the dimensionless counterparts of these couplings that you just get by multiplying them with an appropriate power of the scale, all of these dimensionless couplings start out being constant in the trans-Planckian regime, and then only start to depart from these constant values below the Planck scale. So that's the main idea, was first put forward by Weinberg at the end of the 70s. There was then a certain gap because adequate tools were missing to investigate the scenario in 4 dimensions until the seminal paper by Martin Reuter, who developed functional renormalization group techniques for quantum gravity. And this is where the field then has started to slowly kick off. And by now, many, many people have written hundreds of papers about it, boiling down to compelling theoretical evidence for such a behavior, for asymptotic safety in Euclidean quantum gravity. So this means with Euclidean signature. More recently, the question of, well, what happens if you actually go to the more physical Lorentzian signature is one that has been investigated, also with quite promising results. All right, and so now what will be relevant for this talk is the question, well, where in this whole setup does predictive power come from, and from where do we get predictions for the values at the Planck scale? So for that, we just have to think about effects of quantum fluctuations in terms of screening or anti-screening. So we do have both types of behavior in the standard model. So for instance, in quantum electrodynamics, we have screening, which means if we look at the beta function, so the scale derivative of the coupling, it has a positive coefficient, which means that the coupling will decrease as we go towards lower k. So k here is an energy or momentum scale, so lower k means larger distances. Then QCD has the opposite type of behavior. We have a negative sign here that means anti-screening, so this means the coupling increases as we go to low scales. Now, if you want to achieve asymptotic safety, we just have to balance screening against anti-screening so that we actually get a coupling that becomes constant. And so you can, in principle, do that in 2 ways. The first one would be to start off with the screening term and then have a higher order anti-screening term. And then these 2 can balance out at this value alpha star. That is the value that is exactly scale invariant. But you can already see in this plot here that if you go a little bit away from scale symmetry, you will either be subjected to the anti-screening or the screening effects, both of which drive you away from scale symmetry. So in this particular combination, scale symmetry is sort of an unstable property of the system, and quantum fluctuations drive you away from scale symmetry. And so this means if you require that the system starts out to be scale symmetric at some trans-Planckian scale, nevertheless, here at the Planck scale, you can reach a whole range of couplings. All of these are compatible with requiring scale symmetry up here. And so this is not a prediction. This is a free parameter, or in technical language, a relevant coupling. And so the interesting case is if you just flip around the two. So if you start out with the anti-screening term and then add the higher order screening term, then you have the situation that quantum fluctuations always drive you back towards scale symmetry. And so here, scale symmetry is really a stable property of the system. Even if you kick the system a little bit away from scale symmetry, quantum fluctuations drive you back towards it. And so if you start out scale symmetric up here, you necessarily end up with this particular value for the coupling at the Planck scale. So this is where the prediction comes from. And so then, of course, we need to understand which coupling actually falls into which of the two categories. And we start out with gravity. It turns out that asymptotic safety is very predictive. I told you we have all of the infinitely many higher order operators in the setting, but only 3 couplings, cosmological constant, Newton coupling, and this combination of curvature squared couplings are free parameters, which, for instance, also means that asymptotic safety doesn't solve the cosmological constant problem. You could have many different values of the cosmological constant. The observed one is one of the possibilities, but there is no explanation for it. However, out of the many, many couplings, only 3 are free parameters. All others fall into this category. They're all predictions. So it's a highly predictive theory. However, those predictions are quite tough to test because observationally, the bounds already on curvature squared couplings that we get, for instance, from looking for Yukawa contributions in the gravitational force and in the future, hopefully also from black hole binaries, these bounds are not particularly strong. And so we have a lot of predictions which are not testable simply because we lack really, really high curvature regimes in nature. And so this is where matter comes in. So the rest of the talk, the focus will be on matter and on understanding what does this idea of scale symmetry actually imply for the couplings of matter. All right, so just to set the stage a little bit more, now that I'm connecting to particle physics, just to be completely clear what the connection looks like, I'm not claiming that quantum gravity is dynamically important at particle physics scales. So when the scattering cross sections are simulated or calculated for the LHC, it's an excellent approximation to neglect any effects of gravitons. However, the paradigm that I'm exploring here is that the properties of these particles, let's say, for instance, their different masses, are ultimately determined from the microscopic physics. So it's simply this paradigm that macrophysics ultimately emerges from microphysics. And so various properties of macrophysics, and in this case, macro means particle physics scales, various properties find their explanation in this microscopic regime. And so this is sort of, in some sense, related to, or very similar to the type of swampland ideas explored in string theory. It's the attempt to understand what theories of particle physics or what effective field theories can actually emerge from asymptotic safety. All right, so now let's make this a little bit more concrete. And I will be starting out with results on the sort of heavy standard model, which means all of the gauge interactions, the Higgs, and then the heaviest 2 fermions, the top and the bottom quark. And so these are results that already go back a few years. And then I will look at the lightest fermions in the standard model, the neutrinos, and tell you about results for why neutrinos are so light in asymptotic safety. And then I'll summarize everything, and that will be work that is quite recent, together with Aaron Held, who's a senior postdoc at the École Normale Supérieure in Paris, and Zoe Skiftopoulos, who's one of my PhD students at the moment. And so we took the whole standard model, all of its couplings, and in particular, we then explored what is actually the consequence of asymptotic safety for the mixing matrices. All right, so that's the overview of what will happen for the remainder of this talk. And the central role in all of that will be played by the Yukawa couplings, because the Yukawa couplings of all of the different fermions to the Higgs, those are the ones that determine the masses. All right, so ingredient 1, heavy standard model. So these are the couplings in the heavy standard model. You have the 3 gauge interactions. You have the top Yukawa and the bottom Yukawa, and then you have the Higgs quartic interaction. And this is just a renormalization group flow, so the scale dependence in the standard model without gravity. And so this is why this just looks continuous at the Planck scale. And you see that the abelian hypercharge is actually headed for a Landau pole here beyond the Planck scale, which is one of the signals that the standard model on its own is actually not UV complete. And that is a direct consequence of the fact that the leading order term in the standard model in the beta function for this coupling is actually screening. All right, also within the standard model, of course, the low energy values of all of these couplings are free parameters. We measure them at particle accelerators. We have no clue why they take the values that they do take. All right, now, as we add asymptotically safe gravity, the following thing happens. So we have basically the gravitational interaction that is constant up here and then basically switches off very, very quickly down here, which just means that below the Planck scale, quantum gravity doesn't interact particularly strongly. And after quite a few years of work, also by different people, we figured out that there are long, complicated expressions for the gravitational contribution, which can ultimately be condensed and parameterized in this very simple form, where they just come in at linear order in the beta functions. So the gravitational contribution is always proportional to the corresponding matter coupling. And then it comes with some parameter that is a long function of the gravitational couplings. And the main thing about these is that they do come with particular signs. In particular, for the abelian hypercharge, it comes with a negative sign, which means that instead of running into a Landau pole, this coupling here just becomes constant. And you can also see that this is exactly this combination of anti-screening and then screening that leads to a prediction. And so this is what you can also see, sort of see here in this plot. You can see that trajectories that start out at different values are all attracted towards this predictive trajectory. All right, so the main thing that will be important from the heavy standard model for what I will say later is that in this regime there is a constant top Yukawa coupling, and then there's also a constant hypercharge coupling, and that actually distinguishes the different quark flavors. So gravity, of course, is blind to flavors. Gravity just couples to energy and mass, and so gravity has no clue whether it's coupling to a top or a bottom quark. So if you would just have the quarks and gravity, you would just end up with the same Yukawa couplings for the top and as for the bottom. That would give you the same masses. That would be very different from experiment, where, of course, the top is much heavier. But the hypercharge, of course, distinguishes the flavors because the top has a different hypercharge than the bottom. And so because we have a regime where the hypercharge coupling stays constant, there will always be a distinction between the different flavors within one generation. All right, so these ingredients will come back later. In particular, the constant top Yukawa coupling will become later, and it will become important in a few slides from now. For now, let me leave the heavy standard model and then focus on the lightest fermions, the neutrinos. So this is just a plot of where the standard model fermion masses happen to lie. These are the masses of everybody else, and then for the neutrinos, we only have upper bounds. But even with these upper bounds, we know that there is quite a bit of a mass gap here. And then you could ask why. So how do you even give masses to neutrinos? Well, in some sense, it's very straightforward. You just introduce right-handed neutrinos into the standard model. Then you can write down Yukawa couplings, and then you can give masses through the standard Higgs mechanism. The standard perspective is that that is not a particularly satisfactory explanation, because then the Yukawa couplings have to be of the order of 10 to the minus 13, which is a very small number and has no explanation. It's just picked in order to match experiment. Now, interestingly, in asymptotic safety, that is a bit different. So what happens in asymptotic safety is that the different contributions of quantum fluctuations of matter and gravity nearly cancel out in such a way that if you look at how the neutrino Yukawa couplings change as a function of scale, they change very, very slowly. Just note this range of scales that I have on this axis, right? I'm looking at 10 to the 25,000 GeV. So these scales certainly take some getting used to. But the main point about this plot is that over this range of scales, you can see the lepton Yukawas increase quickly over this range of scales, and they sort of shoot past the neutrino Yukawa couplings, whereas the neutrino Yukawa couplings are, I mean, basically constant over this entire range of scales. And they even decrease a little bit in this range. And so the asymptotically safe perspective is that this number, while we can't predict the exact quantitative value and we can't say exactly, well, the mass has to be this one or this one, we can say it's sort of natural for neutrinos to stay light, or they are dynamically kept small. So if you sort of choose, even if you choose values here, which are already much larger by many orders of magnitude than the values for the leptons, you see that they actually remain here and they don't actually increase further. And so this is a flip of the perspective to the sort of the standard story. In the standard story, you would say, no, 10 to the minus 13 somehow is something that needs an explanation, and therefore we add new degrees of freedom. We come up with seesaw mechanisms. Here the idea is that, yeah, I mean, you do need new degrees of freedom, but actually you only need gravity. And then this number is sort of natural, or it would be very difficult to get Yukawa couplings which are significantly larger. All right, and so the mass gap is generic. The exact values do remain free parameters. All right, and so now with these two ingredients in mind, we can now take everything together, look at all of the couplings in the standard model, and then in particular focus on what is going to happen to the mixing matrices. So the mixing matrices describe basically how the weak interactions mix the different generations and how mass eigenstates mix in the weak interactions. So they give rise to particular decays of mesons. And then in the lepton sector, you have the mixing matrix that is called the PM&S matrix that is at the heart of neutrino oscillations. All right, now experimentally, the values of these matrices have been measured, and here I'm just showing you their relative sizes. You can see that the CKM matrix is nearly diagonal, so not a lot of mixing in the quark sector. And you can see that the PM&S matrix is very off-diagonal, so lots of mixing, large neutrino oscillations. Well, why are these matrices so different? What generates these structures? Basically, the bottom line of what I will have to say is that parts of these structures can be understood as being emergent from a regime with asymptotically safe gravity. All right. Now, how does this work? So let's first of all take a look at the actual experimental values. So this is the CKM matrix, encodes the mixing for the quarks. It is a unitary matrix, which means that in every one of its rows or its columns always have to sum to 1. And so this means there are 4 independent elements. These are their measured values. So just some random numbers, but it just so happens that if you take the elements in the first row and sum them, you get something that is very close to 1. Similarly, if you sum the elements in the second row, the first two, you also get something that is very close to 1. And so the third elements in each row then have to be very, very close to 0. So that's just an experimental observation. And now it's just a mathematical fact that such a relation, this relation here, that is an emergent relation, which means it's an infrared attractive fixed line, or the endpoint of a fixed line of the renormalization group flow. If there is a very long regime, so it has to be highly Transplanckian, which is dominated by the Yukawa coupling and where the Yukawa coupling is constant. All right, so given this experimental observation and this fact, you can take one of two attitudes. You can either say, well, I still think that quantum field theory has a cutoff at the Planck scale. This fact is just pure coincidence. Or you can say, well, somehow these experimental results together with this fact suggests that maybe quantum field theory should continue to hold far beyond the Planck scale, and that the top Yukawa coupling should indeed be constant in this regime. And now, of course, it's your choice which of these options you prefer. Personally, I go with the Sherlock Holmes version that we don't really like coincidences. It's a wasted opportunity. And in particular, of course, I already told you about the fact that in asymptotic safety, if we do look at the behavior of the top of the quark Yukawa couplings, we have this regime with a constant top Yukawa coupling. All right, and now the next slide will have very busy plots. So let me walk you through them step by step. What I'm showing up here are the quark Yukawa couplings. Down here, I'm showing the CKM matrix elements. and I'm showing them over large ranges of scales. We will first just focus on this regime down here. So in particular, what you then can see is if you locate those matrix elements, which have to sum to 1 according to this fixed point relation, you can indeed see that these two do sum to 1, or in other words, this one approaches 1 minus the other element. You can see that this is happening here. And so this is why they end up to sum to approximately 1 at low energies. And then you can also, in the plot, locate the other two matrix elements, the one in the second row of the CKM matrix. And you can see that this one actually is approached by the 1 minus the other one, but only down here. So this relation ultimately is also emergent, but in order to see that, you actually have to look all the way down here. All right, so in this plot, you can see both of these relations ultimately emerge. But you can also see that we not only have this top-dominated regime, but actually there is sort of a cascade of different regimes of actually different fixed points. Here's a bottom-dominated regime. And in this regime, it happens that this second relation here is actually not yet generated. It's only the first relation that already emerges in this regime. The second relation emerges much later. And now in the renormalization group flow, the earlier a relation emerges, the higher the precision with which it holds. And so if all of this here is to be correct and these crazy ranges of scales are supposed to make sense, then it must be the case that the difference of this relation to 1 is much, much smaller than for this one. And this means that this matrix element has to be much, much smaller than this one. And so when we looked at the experimental data, we really had to look quite a few times, because it actually is the case that experiment satisfies this ordering, which you expect from this cascade of fixed points going over these very large ranges of scales. And in fact, the other possibility that would be incompatible with this type of scenario is actually ruled out at 29 sigma. So I think we're probably pretty safe there. Let me just show you the same thing again to show you the same message with slightly different plots. So here I'm just looking at the matrix element, the third matrix element in both rows, and you can see that starting out from some set from some range of values here, the matrix element in the first row is driven towards 0 over this entire range of scales. The matrix element in the second row is first not driven towards 0, but then actually only later driven towards 0. And this is then exactly what gives rise to this ordering that matches experiment. All right, so you can think of this, or we think of this as sort of a fingerprint that this highly Transplanckian regime ultimately leaves in the structure of mixing matrices. All of it, of course, if you're willing to buy this idea that really quantum field theory extends not just up to the Planck scale, but quite far beyond. All right. Very briefly, because I think my time will soon be up. All right. Then let me say something about the PMNS matrix. Because if you just look at the structure of the renormalization group flow for the PMNS matrix, it is equivalent to that of the CKM matrix if you just exchange quarks with leptons. And so now you might wonder, well, if we have this mechanism that drives the CKM matrix to this diagonal structure, are we then not in danger of also driving the PMNS matrix to a diagonal structure and thereby killing off neutrino oscillations and just getting predictions that are completely different from actual experiment? Well, the answer is no, because the neutrino Yukawa couplings that enter the renormalization group flow behave so differently. And so this is where the second result, that neutrino Yukawa couplings automatically stay small, becomes instrumental. So it just so happens that because the neutrino Yukawa coupling stays so small over this whole range, the PMNS matrix elements basically never start to run appreciably. So they basically just stay constant over this entire range. This would be different if the neutrino Yukawa couplings were larger. If we increase the neutrino Yukawa couplings, we start to see a change in the PMNS matrix elements that then start to tend towards a diagonal configuration. And so what we are seeing in this idea of asymptotic safety here is that neutrino oscillations or neutrino mixings are large, because neutrinos are so light. And if we would make neutrinos heavier, somewhere heavier than the 1 to 10 electron volt range, we would be driven towards a diagonal PM&S matrix. All right, so there's this structural connection between two properties of neutrinos that in this paradigm is due to quantum gravity. And so to sum this story up, some of the structures that we observe in the standard model emerge from this trans-Planckian regime with quantum gravity that is ultimately governed by quantum scale symmetry. Not all of the structures of the standard model, and of course there are also caveats to these calculations. They are done in certain approximations or in a certain parameterization. They mostly rely on Euclidean renormalization group flows, so there is still some work for us to do. But what this ultimately amounts is that in this picture, you really have to think differently about new physics beyond the standard model. So, of course, experimentally, we might hope for new physics to be just around the corner. But if these explanations here actually are to work out, then new physics, except for gravity, should really just be in separated sectors, of course, for dark matter, but must not interfere with this picture very much. And now I'm run out of time. The next few slides would have been about dark matter. Feel free to ask me if you're interested.